I'll plan to send him an email.
Okay.
And if I don't get anything back from that in a few days, I'll make sure to reach out to you. Thank you so much.
Because yeah, we're all doing the same wet chem labs, and we're all doing the same give data, pictures, videos for a particular set of the labs that are dry, that are basically just simulation observation stuff. It's complicated. I really wish it was not this complicated.
It is what it is.
Anybody else have lab questions? All right, let's go over homework, and then I will talk about the test.
For my homework, I had sent you a comment about when I tried to submit a new file.
Okay.
And I see that you had wrote me back and you said that
I opened up both files. I opened up the one that was attached, but then I opened up the one that was like a secondary one, and they didn't look different.
Because I opened it up on my computer and it's different, so I don't know how come the one that you got wasn't different. Because if you I don't know how to show you.
So send it to me, not through Canvas. Send me your alternate version via either my regular email at work, which is the amoller.tcc.edu one, or you can send it to the Verizon one. If you send it not through Canvas, maybe that will allow me to see a different document.
All right, I'm sending it to you now.
Okay.
Right,
and I will look at it after class then and see if I can see it as a different document then.
Okay, thank you.
Yeah, there's this never-ending litany of tech problems where things either don't work the way they're supposed to or don't work at all sometimes. All of those fun things. Other questions before I see if I can do the screen share for the homework set? Okay, so screen share. All right. So the first bit here was just balancing. When we look at the first one, that one's really pretty straightforward. One of the more obvious things that you first see is, oh, there's 2 hydrogens in the water molecule, and prior to balancing, there's only a single hydrogen on the nitric acid molecule. So you need to insert a 2 in order to make it balanced there for your nitric acid. For the second one, this one requires 2 corrections. Because on the left-hand side, my CH4 molecule has 4 hydrogens in it. But then on the right-hand side, what the products are, I have a molecule of CCl4. This kind of brings up the idea that, oh, I actually need 4 of each. I need 4 hydrogens, and I need 4 chlorines minimum. But in order to make everything work out, since the chlorines are only in diatomic molecules to start with, you ultimately need a 4 for the Cl2, and you need a 4 for your HCl molecule. The last one there was the messiest one. Because you have hydrogens on the product side, both in the CH4 molecule and in the aluminum hydroxide molecules, you actually need quite a large number of them for your waters. You need a 12 there in order to give you enough so that you can have a 4 of the aluminum hydroxides and a 3 for the CH4s, and that gives you a total of 24 hydrogen atoms. All right, the next one involves the concept of solubility. The idea here was to make sure that you were not disassembling polyatomic ions. The first one splits in half to give you a single copper 2 ion and then a sulfate, the SO4 - 2. The second one also splits basically in half, 2 pieces, one of which is the sodium ion, and the other one is the acetate ion. And the third one, and I saw a couple of glitches on this when I was doing grading, your 2 potassium ions do not stay stuck to each other. You cannot leave it as a K with a sub 2. The 2 has to become a coefficient once you've put this in water and it's become soluble. Then we move on in the direction of what precipitates will possibly form. Now remember, in doing this, since we're not actually writing equations at this point, the goal is to make neutral molecules. AgCl2 is not a neutral molecule. In order to have it have no leftover charge, you need a single silver, because silvers are always and forever +1, and you need a single chloride. The other chloride is just swimming around in solution, not being used currently. So silver chloride is your solid. For the last one on that page, even if you did the switch, even if you did K2SO4 and NH4Cl as your possibilities, if you go back and you apply the solubility rules, nothing makes a solid. Everything stays soluble. This is to give you a little hint here that there are times, and we talked about this a little bit a week or so ago, that no precipitate actually occurs. Everything just stays swimming around. All right, the next one is meant to kind of lead you along through the process to kind of get you in the groove for how many steps you need to think about here. First, I'm going to split my 2 molecules. Again, I'm trying to keep track of charges and how many's. My sodium carbonate becomes 2 separate sodiums, each of which has a +1 charge, and a carbonate, -2 charge. The lead is the +2 version, and I have 2 nitrates. So then I began to do the first and last and third and second mechanism. And my balanced molecular should have sodium carbonate and lead nitrate, gives you 2 sodium nitrates, don't make the 2 subscripts, make the 2 a coefficient, and 1 lead carbonate. It doesn't actually matter which of those 2 molecules you put closest to the arrow. That doesn't actually make a difference. You could have written PbCO3 plus 2 sodium nitrates. The order is not relevant. So then, complete ionic. Everything that is soluble splits apart. So this kind of goes back to what you saw there in step A. Everything is in pieces on the left-hand side. We've got 2 sodiums and a carbonate and a lead +2 and 2 nitrates. But because the sodium nitrate is not a solid, not your precipitate, it falls back apart on the product side, and that leaves you with the only unionized molecule is your lead carbonate. If you get rid of, I scroll down weird. If you get rid of all your spectators, if you get rid of your sodiums and you get rid of your nitrates on both sides, your leftovers are your net ionic. Positive thing plus negative thing equals molecule. That's the pattern we see. In this case, the positive thing is your lead +2. The negative thing is your carbonate, and then it makes a lead carbonate molecule. When you get to number 7, this one, having sort of walked you through the process, I just gave it as a single problem, and you can just sort of do it all in a couple of steps. Molecular, I gave you the reactants. We have NH4S, which is my ammonium sulfide. You have cobalt-2 chloride. Do your swap. You get 2 molecules of ammonium chloride and 1 molecule of cobalt-2 sulfide. You would have to then go back up and look at your solubility rules, and the NH4 containing molecule is not a solid. The cobalt sulfide is your precipitate. And I didn't ask you for a complete ionic in this one. I only asked you for a net ionic. Pick your cobalt sulfide, bring it down, put it on the right-hand side. Take your 2 pieces that it took to make that and put them on the left-hand side. One habit that I saw several people do, if it says write the equation, you need to show me both the reactant side and the product side. A few people only wrote the product side, which, considering a couple of these needed balancing, kind of made it incomplete. Then we switch over to acid-base reactions. Yes.
Just checking. I actually did write out the complete ionic, and then I condensed it to the net ionic. That wouldn't be marked wrong.
No,
I know
that's
you only
just
showed it
that's just showing me the step in between.
Okay.
So yeah, that's fine.
Okay. Cool. Thank you.
You complete ionic is a useful step, but sometimes not a required step, depending upon what the question asks for. It's like you can show your work, and I'm going to look at the things that I specifically ask for. All right, acid-base stuff. You had to balance the first one because it needed a 2 out in front of your hydrochloric acid, which then gives you 2 water molecules, and the salt of that particular reaction is your calcium chloride, CaCl2. On the other one, no balancing is needed on the left-hand side. I've got a sulfuric acid molecule and a strontium hydroxide. You get 2 water molecules again, and your salt is your strontium sulfate. Then we get to gas generating. Sodium bicarbonate, NaHCO3, and hydrochloric acid. Once you add the 2 of those together, the sort of the tip-off that we talked about in terms of patterns is a carbonate or a bicarbonate with an acid gives you a salt, a water, and a carbon dioxide molecule. Now, in this case, we kind of literally have salt. We have sodium chloride, but you also have a water molecule, and you have a gaseous CO2. Oxidation states. Note the instructions say do the oxidation states for each element. In the past couple of days of grading, a few people did not give me all of the elements in each of the molecules there. Cl2, pure element, so they have to be 0 oxidation number. MnO2 is a neutral molecule. Oxygens are -2 each, and yeah, there are 2 of them. And that makes your manganese worth plus. Yeah, no, I have a goof. That's supposed to say +4.
Yeah, I was gonna say.
Yeah,
2.
no, I just realized I wrote the wrong number in there. I'll have to go back and see if I can correct this and repost it. Let me make myself a note. This is, it's like all these things where I translate over from stuff I've written by hand. Because normally I do this on the bored and all that sort of thing. So, yeah, in typing, I've made some goofs. Yeah, that should be MnO. MnO2 should have a manganese that's +4. The one below is correct though, because MnO4 minus is not a neutral molecule. You should have one negative left over. That makes your manganese worth +7. For the bicarbonate ion, again, not a neutral molecule. You should have one negative left over. Hydrogens are their normal +1. Oxygens are each their normal -2. And your carbon is a +4, because that's what you have to make everything else work out. And then xenon hexafluoride, the xenon is a +6, and each of the fluorines is a -1. So yeah, I have to go back and fix the one manganese that I goofed there. All right, more redox stuff. If you go through and you write down the numbers, the oxidation numbers for each of your elements, as you are going from left to right, your iron starts out as a +3 when it's part of the iron oxide molecule. But on the right-hand side, it is neutral, so it's going from +3 down to 0, which means your iron has been reduced. Now my carbon, on the other hand, started out life stuck to an oxygen, which made it worth +2. On the product side, it's stuck to 2 oxygens. My carbon's worth +4. Carbon is oxidized. It does also ask you, it says an ID, identify the oxidizing agents and the reducing agents. So remember that they're backwards. Thing that got reduced is oxidizing agent. Thing that got oxidized is reducing agent. And actually nothing happened to the oxygens. If you went through and you numbered all of your oxygens, every single oxygen in the entire equation is worth -2. Oxygen didn't get oxidized and it didn't get reduced. Then we move on to stoichiometry. This is another one where part of this is trying to sort of lead you along to get you used to the idea of looking at all the different parts of the equation. Your equation has 5 F2s and 2 NH3s as their reactants. The mole-to-mole ratio, and note, find and know. I'm trying to find NH3, therefore it should go on the top of my fraction. And my F2s are known, therefore they should go on the bottom, along with the appropriate coefficients. You have a 2:5 ratio of NH3 to F2. So then I backed up a little bit. Well, what if you're starting with 25 grams of fluorine? Note, it's an F2 molecule, so you have to add the 18.99 twice so that you get a molar mass of not quite 38. This will give you 0.659 moles. So take the information from A and the information from B, apply them together, and this tells you that you would need 0.2636 moles of NH3. All right, switching gears just a little bit. What if you're looking for a product now? One of the products was HF. Different ratio. I don't know if you guys can see where my cursor is here, but the 6 and 5 are your new ratio. It's no longer a 2:5 ratio. It's now a 6:5 ratio. Take the number of moles that you started with, your 0.659 of fluorine, multiplied by 6/5, and you will get 0.79. What if it was grams? If it was grams, you need to multiply by a molar mass. Molar mass of HF is 20. So you would end up with 15.82 grams. What if we wanted to find the other product? You can actually string all your data together here. Thing you know, 0.65 moles of fluorine. Different ratio. This one is a 1:5 ratio because it's all about the balanced reaction. N2F4, a little bit heavier. We have a molar mass of 104. You ultimately get 13.7 grams. So all of those pieces are tied together. The ratios are crucial. The next one is a limiting reactant problem, of which, okay, I realized I didn't put my last line in here. Actually, maybe it'll let me go back and fix this. Hang on a minute. Let me see if I can go back and fix this, and then all I have to do is reload it. Let me go back and see if I can fix, because this is a document that's open on my computer. Maybe it'll actually let me fix it while I'm, yeah, okay. Fix it while I'm talking about it. All right. This is missing, for some reason or other, I don't have the last line shown here. The last line should be 40.8 times 0.95 because it said 95%. That should give me, because I knew the answer is supposed to be 38 something. 38.76, yeah, grams. No, undo. Okay. Trying to make it turn red so it actually looks like the rest of the answer. somehow or other I didn't type in the last part there. Okay, so you have two reactants and you know the mass of both of them. You have to do the grams to mole conversion twice. Once for the potassium platinum chloride, which has a really massive molar mass of 415. I get 1.36 moles. I have 36.6 of the ammonia. Ammonia doesn't weigh very much, it's 17. I've got a little over 2 moles. I assume that my actually, did I do this one wrong? Yeah, okay. Yeah, okay. I didn't do it wrong. My decimal's in the wrong place. This is supposed to be 0.136. Yeah, I put my decimal in the wrong place. Because it's down here. It's like you can see the 0.136 down here, and I realized I glitched that. So anyway, 34.6 of ammonia divided by 17 gives you 2 moles. I have a lot more ammonium than I have my potassium platinum compound. Your K2P2 Cl4 is your limiting. I have a 1-to-1 reaction here. For making the product. I actually don't care how much KCl I'm getting. That just happens to be something else as part of the equation. Multiply by 300. If everything had gone 100% perfect, I would have got 40.8 grams. I got 95% of what I thought I was going to get, which is why I needed that last step there of put the .8 times 0.95, because that's 75%, gives you 38.76 grams. The ones below, you don't need to figure out how much you're going to make. All you need to figure out is which one you're going to run out of. It is usual to test the small one. So of the first pair, I've got 1.4 and 5.3. So I'm going to assume that maybe my aluminum is my limiting. And I test it against my ratio. 3-to-2 ratio. I need 2.1 grams, 2.1 moles of chlorine. I've got 5. So yeah, my guess was correct. But when I do the next one, I assume that my oxygen is limiting because I've got less of it. It's 3.4. But when I do my 2-to-1 ratio, I actually would have needed 6.8 of hydrogen. So my guess was wrong. It's not the oxygen that's limiting. It's actually the hydrogen that's limiting. And then the bottom one. I'm again testing my smallest one, 0.48 moles of P4O10. I have a 6-to-1 ratio for this one. If I use up all my P4O10, I need 2.88 of the water, and I haven't got that much. I've only got 1.5 moles. So it's not the P4O10 that's limiting, it's the other one. Each time you pick one, you must compare it, and then you need to figure out, do I have enough? Or would I have run out? You have to do the test because sometimes, like the first one, letter A, sometimes the smallest one is the limiting one. But on the bottom two, on B and C, it's not the smallest one because it has more to do with the ratios of your balanced equation. And then the last one is just kind of one full problem, but you also have to balance it too. You need 6 sodiums, 1 N2 molecule gives you 2 sodium nitrides. If you start with 10 grams of sodium, divide by the mass of sodium, 22.99, you get 0.435. 2-to-6 ratio. My Na3N molecule weighs 82.98. Ultimately, I would have gotten, theoretically, 12.03 grams. Questions?
That one on number 15, you got the 6. So when you balance that out, can you run through that for me real quick? How you got the 6?
So I've got 2 nitrogens over here on the left-hand side. And according to this molecule here, Na3N, I can't have any less than 3 sodiums because it takes 3 sodiums to make 1 molecule. But I have this problem of, since my N2s only come in pairs, I really need 2 entire molecules. So that's going to be big 2 times little 3.
Okay.
Which means I need 6 in order to make it be balanced.
Gotcha. Thanks.
Other homework questions? I'm gonna unshare that. I'm gonna save my corrected version, and I just got to remember to post the corrected version where I fixed the manganese thing. Because I posted the answer key this afternoon, but obviously I had a little glitch in it, so I need to go back and repost that. All right, let's talk about the test as a whole. And let me pull up my whiteboard because that's probably the easiest way to do that. Okay, so this is a 2-chapter test. And the beginning part of this chapter goes back and starts with weighted averages again. That was one of the things that we talked about in chapter 2, and then we kind of ignored it for a while, and it popped up again at the beginning of chapter 3. So you recall that, go back and check your homework. Weighted averages are something you're going to see. We then also did from grams to moles, but also to atoms or molecules. So make sure you can go back and forth between them. Again, homework is a good clue here of if you start with grams, you need to be able to convert to moles. If you start with moles, you need to be able to convert to grams. But then there's also the atoms, which makes use of Avogadro's number, 6.022 times 10, and it won't, actually probably won't let me do an upscript here, but we'll do it this way. We'll do the caret thing. 6.022 times 10 to the 23rd. That's your important number. You need that number if it asks you how many atoms or molecules in moles, because it's the conversion for those. We also did the same thing with entire molecules, which then also means you need to know how to do molar mass. Things like if you had, let me think up one here, magnesium silicate. Okay, you have to add one of your magnesiums plus silicon plus 4 oxygen molecules. All this is periodic table information. So make sure that when you sit down to take the test, you either have your textbook flipped open or you can use the one inside your lab book. You're going to need the periodic table for a batch of different things here. We also did percent by mass. Remember that percent by masses are an idea where you have all the percentages must add up to 100% if you do them for the entire molecule. That's one of the ways you can kind of double check yourself up to a degree of thinking about, okay, well, if it was 15% sodium and 80% silicon and I had 5% left over for my fluorine, yeah, that all totals up to 100%. We also did empirical, oops, did not hit return there. Empirical formulas. What happens if I spelled that remotely correctly? So empirical formulas, which then also went over to molecular formulas. Again, this is kind of a go back and look at your homework thing. If you can figure out an empirical formula and you know what the molar mass is, you can determine whether or not your molecular formula is the same or different. We also did, as part of this chapter, some solutions. We did molarity. And we did percent by volume. We also did dilutions. Remember, dilutions are M1V1 equals M2V2, obviously with subscripts. And there was one of those also in the homework set. And that was kind of the end of the chapter 3 material. So then we can switch over and move on to chapter 4 stuff. Let me add, yeah, okay. So chapter 4 stuff. Next. All right, so we began this chapter primarily with the balancing. So make sure that you are paying attention to such things as subscripts when you are doing balancing. Then we began to talk about solubility. Solubility being a feature where you are trying to figure out, okay, according to the 6 rules, which things are soluble and which things are not soluble. This leads us toward predicting precipitates. It would help if I spelled that remotely correctly. Which then led us over into the fact that there are 4 main types of reactions, at least according to what we covered. So we did precipitation reactions. We did acid-base reactions. We did gas generating. And we did redox. So backtracking a little bit then. For the precipitation reactions, we did molecular equations. Molecular equations need to have a reactant side and a product side. We did complete ionics. One of the features of the complete ionics is the only thing that doesn't have charges is the one item that is solid. And then as kind of the crowning glory to that particular set, we have net ionics. Then we talked about acid-base stuff. Okay. Acid-base stuff has salt and water as products. Keeping in mind that your H's and your OH's need to match in order to make this balanced. We did oxidation numbers as a prelude to redox equations. And then we switched gears a little bit and we did stoichiometry. The main goal of stoichiometry is to keep in mind things as grams usually need to be converted to moles, which then usually need to be dealt with a ratio, which then gives you other moles. And then for this chapter, we're usually going back to grams. It's a process. 3 main steps, but even when you're doing limiting reactants, you have the same sorts of steps. And I think those are all the main topics. I have totally lost track. It took me probably 12 hours to type the test because of the fact that Canvas is so unwieldy. There's roughly the same number of problems that were on the last test. It's slightly unbalanced in that because chapter 3 was a shorter chapter, there's somewhat less questions regarding chapter 3 than there are chapter 4, just because the chapters were not really the same length. Fair number of problems where you have to input values to give me answers. Show work when possible. There's also, trying to think what else needs to go with this. There's some multiple choice. There's a few true false. I gave you a few where you need to tell me which type of reaction it is. Okay, we covered 4 main types, but we also talked about what tips them off, what makes them look the way they do. So I think there's around 40-ish problems on there. Each one, of course, has a point value next to it. There's some buzzwords thrown in a couple of places. I think those are all the main highlights. You have from basically midnight tonight / midnight tomorrow morning, kind of thing, all the way until midnight on Monday. So you have a 4-day window to take it. But like the previous test, once you start, you have 4 consecutive hours, and then it'll lock you out of the system. Same lockdown browser thing. You log in through the lockdown browser. You can use your textbook. You can use your lab book. You can use your homework. You can use your notes. You can't surf. You can't use each other. Questions?
Chapter number 4, and that's it, right?
This is chapters 3 and 4 is the test.
3 and 4, okay.
Yeah, chapters 3 and 4. All the tests this semester are approximately 2 chapters. The 4th test, the one that occurs kind of right before Christmas break, is 2.5 chapters because there's a couple of sections that end off another chapter that we're going to hit on, but all of the other tests, not including the final exam, are just basically 2 chapter tests. Other questions about topics for this test? Because I think I don't want to get into deeper into gas laws tonight. I want to give you guys a little absorption time so you can go take the test, and then we'll return to gas laws on Tuesday.
You have both.
And some of you, I will see you on Monday.
You have both of the answer keys for the homework on the
number 3. Yeah, number 3 is already loaded.
Okay.
And like I said, number 4 is on there, but I need to, when I get off of here, I need to repost it because it has that one glitch on the magnesium letter. But I'll get it. I'll like replace the file, so you should be able to go back and have a look at those.
All right, thank you.
Okay, other questions regarding homework or test topics?
Not quite a question about those.
Okay.
So when we get back, we're going to be doing chapter 9.
Yes, which is gas laws.
And I know this is looking forward, but what are the next 2 chapters? Like it won't. So is it 9 and like 4? Or?
Gas laws is 9, and then we hop back to chapter 5, which is thermochem. And then after thermochem, chapter 6 is what's referred to as quantum, and 7 is Lewis structures and molecular geometry, with this little smidge of stuff from chapter 8, which actually goes with chapter 7 because it's all the same big topic. And so that makes the final test of the semester is chapters 6, 7, and a tiny slip of 8. Thermochem and gas laws
Okay.
go together as the third test. All of the notes have already been loaded. All of the notes are already available. Okay, so if you want to like scroll down that the page that's there on Canvas, if you hit the view all pages and it shows you, I really wish it would let me not do them alphabetical, but yeah, I'm stuck with the way it is. At least I haven't found any way to not make it be alphabetical. But if you go down and it says notes for all chapters, and so there should be all of the documents loaded in there for everything that we're doing this semester, because I was trying to make sure I got that done like in the first month of class so that people can see what's coming. Other questions? All right, like I said, I don't want to get it further into gas laws tonight just because the test is this weekend. So I want you guys to focus on that. All right, and I will see some of you on Monday for lab because we are doing hydrates this week, just like the other half of my people who did hydrates this past Monday. And the rest of you I will see on Tuesday. Bye.
Bye.